I'm building an open source microcontroller board clocked at 1 GHz. Today, we're writing our first program, porting a real-time operating system, and seeing how well the onboard IMU tracks movement. Getting the first program on this board is actually fairly complicated. To allow the user to both program and debug the main microcontroller, I'm using a small secondary microcontroller running firmware called DAPLink. This means that I have to program this chip before even thinking about writing a Hello World program. To program this chip, you have to use these small pads on the back of the board. To connect to them, I'm using these fancy PC-Byte probes and an MCU Link Pro debugger. To get started, I cloned the official DAPLink repo and checked out the latest release. Building the default firmware image for this chip was thankfully pretty easy, however I do need to make some customizations, so I went ahead and created a fork where I can add my board-specific code. First, I edited the project.yaml file, which tells DAPLink that my board exists and points to any other configuration files. Next, I created a record file that sets some macros and points to the source files. I also created a record for the bootloader firmware. Both of these point to an I/O override header where I modified some of the pin numbers and added these boot mode pins. The two C files are where the custom logic lives. The bootloader's C file has some extra code for initializing the boot mode pins and adding a pull-up resistor to the software reset pin. Finally, there's the G2 Nano.c file. The main addition that I made involves the target microcontroller's boot mode pins. In theory, you should be able to program this microcontroller without messing with these pins, but if programming is to fail, then there's a chance that it can leave the microcontroller in an unresponsive state. To prevent this, it's best to reset the microcontroller into serial downloader mode before programming, then reset it back into internal boot mode once you're done. To achieve this, I created a custom vendor command that tells DAPLink to set the boot mode pins and reset the target microcontroller. To test it, I wrote this short Python script. When I set the boot mode to 1, you can see that the boot mode pins change to 0, 1, and the reset signal is asserted for 1 millisecond. If I set the boot mode to 2, the pins change to 1, 0 before pulsing the reset pin. Of course, this chip will come pre-programmed, and you won't have to worry about what commands are being sent under the hood. That being said, if you are designing your own board, then you're more than welcome to reuse this firmware. Everything is up on GitHub. Finally, we can start thinking about actually programming the board. I figured it would be easiest to start with the vendor's official toolchain, so I went ahead and installed MCU Expresso for VS Code. I created a new project and wrote a short program that blinks the user LED. It might not look like much, but this is a huge step. The coolest part is that the code isn't just running, this is an interactive debug session. That means I can set breakpoints and even step through the code line by line. How cool is that? Now that we know the board's work, we can start porting the Zephyr real-time operating system. I created an empty folder to use as my Zephyr workspace and ran all of the commands from the Getting Started guide. 9 GB later, I'm ready to start working. To port the board, I created a ThetaMachine/dev G2 Nano folder in the boards directory. The board.yaml file contains some metadata, and these two kconfig files tell Zephyr which processor I'm using, as well as my board's default software configuration. You'll notice that I'm using the 1176 version of this chip, even though the board uses the 1171. This is because Zephyr doesn't currently support my exact chip. Not a big deal, I just have to port it later. Thankfully, the 1176 is close enough to get started. Since the microcontroller uses external flash memory, I have to do a little extra work to set up the communication. That's done with this flexby.nor.config.c file. Thankfully, I didn't have to write this from scratch. I started with a similar file from NXP and modified it to work with my board. To include this file while building, I added it to the cmakelist.txt file. I also added this flag that enables XIP, or execute in place. This allows the processor to run code directly from flash without having to copy it into RAM. Next, I have to define all of the hardware-specific details by creating a device tree file. For things like the LED and button, it's as simple as just telling Zephyr which pins to use, but the device tree can do so much more. For example, the default device tree for this SoC defines multiple memory regions, which I don't really like for this board. There's nothing wrong with it, but I want the on-chip RAM to appear as a single contiguous block, so I deleted the default nodes and created my own that's 1.5 megabytes large. In case you're wondering, the other half meg is dedicated to tightly coupled memory, with 256 kilobytes dedicated to instruction TCM and the other 256K dedicated to data TCM. I also defined the QSPI flash chip's hardware interface. While this is far from being finished, it should be enough for us to compile the Blinky program. It compiles! To flash it, I want to be able to use Zephyr's meta tool, West. For this, I need a couple more files. This one tells West to invoke PyOCD and points to my custom script. The script sends that DAP command from earlier to make sure that the microcontroller is in the correct mode for programming. After programming is finished, it resets the microcontroller back into internal boot mode. And voila, we are once again blinking an LED. This is cool, but I think we're ready to write a proper Hello World app. Thankfully, this is much, much easier now that we've done all of this setup. I plan on writing multiple apps in this video, so I'll create a directory called apps. This is a Hello World app, so I'll create another folder called Hello World. Zephyr requires us to create 3 files. The first one is a prj.conf file. This is where you set custom kconfig settings, but we can leave it blank for this project. Next is a CMake file that tells Zephyr how our source files are organized. Finally, the app itself lives in main.c. I'll use this struct to grab the button's pin information from the device tree, and I'll initialize the pin here. Now I want to configure a callback function that gets called whenever the button is pressed, so I'll create a GPIO callback struct and add the callback here. This points to a function called buttonISR, so I'll create it and have it print Hello World. That's it. Now when I click the button, it should say, close enough. Alright, it's time for the main event. I want to use the onboard IMU to track the board's orientation and have the 3D model follow it. This should be relatively easy since Zephyr already supports this IMU. Before writing any code, I need to add the IMU to the device tree. Now I can write a simple program that pulls the IMU and prints the orientation. It works! For the 3D model, I wrote a quick Python script using Panda3D. This is really cool, but it reveals a key issue. You'll notice that the tracking isn't exactly perfect. It's definitely moving when I move the board, and it's moving in the right direction, but the orientation drifts really quickly. That's because gyroscopes don't give you orientation directly. Instead, they give you angular velocity. To get orientation, you have to integrate this number over time. Unfortunately, this isn't very accurate, especially as time goes on for longer and longer. To make the orientation estimate more accurate, you can combine the data from the gyroscope and the accelerometer. This is called sensor fusion, and the basic idea is that at rest, the accelerometer is essentially just measuring gravity. This tells us which way is down, which we can use to help compensate for any drift. Now, sensor fusion is a really cool but often complicated subject. One of the most basic types of filter is called a complementary filter, but you could fill textbooks with the other clever ways people have found to fuse data together. Thankfully for us, this board's IMU handles sensor fusion for you, and it does a pretty dang good job at it. I'll write a program that uses the IMU's SFLP block and reports the data at roughly 30 samples per second. This program is a bit more complicated than the last one, but it's not too bad once you understand what's going on. Basically, the IMU has an interrupt pin that tells us when to sample its FIFO. Our code simply gets here and waits until the interrupt is fired. Then it samples and prints the data. One big change is that we're no longer outputting Euler angles, or 3 angles around x, y, and z. Instead, we're outputting the orientation as a quaternion. Quaternions often get a bad rep for being complicated, but bear with me, they're super easy to work with. A quaternion is just a convenient way to encode a rotation. You define it with 4 components. You've got this magic scalar w and a vector. The direction of this vector defines the object's axis of rotation, and the magnitude of this vector encodes how much the object has rotated. That's it. The rest is just arithmetic. You might be asking, what about w? Well, the IMU reports a unit quaternion, meaning w can actually be defined in terms of this vector. W makes the math easier, but it doesn't really carry any information, at least not for this application. That's why the IMU can leave it out. I do have to quickly update my Python script to use quaternions, but that's fairly simple. Quaternions are ubiquitous in 3D graphics. Whoa, that's awesome! This is so much better than before. This board makes me so excited. I think this is one of the most fun projects that I've ever worked on. I hope this video doesn't make the board look too complicated. Trust me, lots of super easy to use boards have crazy firmware running under the hood. This is just a peek behind the curtain. Anyway, if you made it this far, consider subscribing. We still have a ton of work to do. We still have to write Wi-Fi drivers, port micro ROS, look into MicroPython, and so much more. I also want to talk about the mysterious motion control IC from last time, all in future videos. I'll see you next time.